this lab is Dijkstra's algorithm. It's kind of similar to the maze solving algorithm, except now your job is to find a path through a city, and it's going to be the shortest path through the city. So you're trying to get from one side of a city to the other side using the least amount of time. So, like I said, the lab evaluates traffic in a city, and one of the hardest parts about this lab is creating the graph structure from the city definition. The cities are given to you in terms of the intersections, so the file you're given specifies the intersections at each of the streets and avenue crossings. So in this city, you have streets, and streets travel from east to west. So you have streets that travel east to west, and you also have avenues. So these are streets. And then you have avenues, which travel north-south. And this is kind of similar to how Manhattan's laid out with its streets and avenues. So by convention, in this problem, all the streets and avenues are numbered starting at 0. And by convention, streets will ascend from south to north, and avenues from east to west. So the streets start up with 0, 1, 2. Oh, so that'll be the avenues. And then the streets start off with 0, 1, 2, 3. So that's how the streets and avenues are numbered in this city. And then in this city, there's also rules about which direction you can travel on the streets. Some of the streets are bidirectional, and some streets you can only go one direction. So even number streets and avenues are always in ascending order, and odd numbers are always in descending order. And then there's some exceptions, and the exceptions are that avenues and streets that are multiples of 5, you can travel in both directions. This includes 0. And the highest avenue always goes in both directions. So in this case, street 0, you can go both directions. Street 1, you can only go in the descending direction. Street 2, only in the ascending direction. And then street 3, only in the descending direction again. And then for the avenues, 0, you can go both directions. 1, you can only go in the descending direction. And 2, since it's the highest avenue, you can go in both directions. And then also in this city, there are intersections at each of the there are street lights at each of the intersections, and the street lights have a location, an XY coordinate, and they also have times that the light is green for the street side and for the avenue side. So for the street side, you can have a time like 3 for it to stay green, 3 seconds. And then on the avenue side, you could have 4 seconds for it to stay green. So you're given a file that specifies all of these intersections, and the intersection is specified with a street and avenue number, which identifies where, like which street and which avenue that intersection is a part of. It defines the XY coordinates of that intersection. So each of these locations could be in different locations, which could cause streets to go at a diagonal. So even, avenues to go to diagonal. So even though this is Avenue 2, for instance, the intersections occur at different points, which causes the road to go at a diagonal. All the roads have to be straight lines, so you're not going to get any roads that have curves in them. It's just going to be a straight line from one intersection to the next. And that makes it easier to calculate the distance and then the time that it would take for you to travel that road. And then the last thing you're given is the time that the light is green for the streets and the time that it's green for the avenues. So street and avenue are integers, and the other parameters are doubles. The units of x and y are in miles, so it tells you the miles from those two, miles of those two locations. And then the units of Green Street and Green Avenue are in seconds. And the intersections can be specified in the text file in any order. So here are some example cities. In this first city, you have 2 intersections or 2 streetlights. One of them's at 1, 3, 1, and the other one's at 1, 1. So between the 2 streetlights is 0.3 miles, if you do the distance between those 2 points. And then for the time, you have 9 seconds on the street side, 12 on the avenue side, and then 3 and 4. So that's the time of the green light and the red light, or the green lights from each of those directions. And then you can also have larger cities, and here you can see how the first 2 stoplights aren't on the same y coordinate as the last stoplight. So then you have a diagonal in this city. And then for calculating the distances between the stoplights, you can use the distance formula, which is the square root of the 2 locations squared, and that will give you the distances of the segments. You can also be given the intersections in more of a random order, but you always have intersections at each of the cross points between the streets and the avenues. So your job, like I said, is to write Dijkstra's algorithm to calculate the fastest path from the light 0, 0, so this would be your start in this corner, to the maximum street and avenue light. So you're trying to get from here to this location. And you also to assume that you travel each road segment at exactly 30 miles per hour. So you can use the speed limit and the distance to calculate how long you'd spend on that road segment. And you can also assume that you can speed up instantaneously and stop instantaneously, so you don't have to account for the acceleration and deceleration time. You can assume that once the light's green, you're instantly traveling at 30 miles per hour down the road segment. So when you call the program, it's called with CityMap. The next thing you're given is how you want to calculate the time. You can either none, which doesn't calculate the path through the city, or you can say best, which is the best time you can travel through the city. And this is assuming that you always have green traffic lights as you're traveling through the city. So it's the best possible time the lowest time you can take through the graph. Then you also have worst, and that assumes that all the lights turn red as soon as you get to them, and you have to wait the maximum amount of time at each of the stoplights. Then you also have average, which kind of averages the time that you'd wait and allows you to take the average, basically the average time through the stoplights. And the formula that he wants you to use to calculate the average wait time is shown. Then the next argument you give is time, which just prints out the time it takes you to get through the city. Print, which will print out the nodes and edges along with the path that you take. And JGraph, which prints out a graph of the city and the path. Okay, so now you can see some examples of him calling the program. With none and print, it just prints out the intersection and the edges, so the adjacency list of each of those intersections. So now he's doing some shortest path calculation. In City 1, where you just have the 2 intersections that are 0.3 miles apart, the best time is pretty easy. It's just the time it takes you to travel the 0.3 miles, which is 36 seconds. The worst time adds 4 seconds because the light could turn green for Avenue 1 as you arrive, and you have to wait 4 seconds for it to be your turn again. And then also you can calculate with the average time, which averages the time that you'd wait at the light and gives you an additional delay of 1.14 seconds. And then when you say print, you also specify the path. And really you do that by just filling in a path variable inside the class, and then he'll take care of all the printing. And then, so here it talks about the calculations for City 2. But basically what JGraph prints out the actual graphs of it. And depending on the times you have to wait at the stoplights, sometimes the shortest distance from start to finish is not the fastest, because you could end up spending longer times waiting at each intersection. So if none doesn't print out a path, best will choose the shortest distance through the city. Worst will basically wait the stoplights, the time you spend at each stoplight. So the worst case is actually longer distance, but it's faster because you have to wait less time. And then average is somewhere in the middle where it assumes you don't have to wait the complete time for each stoplight, just an average of the times. And then for City 3, it's interesting because the best is shortest distance through it. Worst, you actually end up taking a zigzaggy path through the city based on the stoplight times. So you actually spend less time driving if you have to wait the worst amount of time for stoplights if you take the zigzag path. And then average, it chooses another path based on the stoplight times. And then you can also define some weird cities where the distances of some of the stoplights are far away from the other stoplights and kind of skews the grid shape of the city. But either way, you still have to be able to you can still find the paths to the best, worst, and average time through it. And then you can also get to some graphs that have kind of random positions too, and it's kind of scattered. And then it also gets denser, so you can have really dense cities. 7's too dense to show an image of. And then you can also, but 9 you can see, and it's a very dense city with lots of stoplights, and the program can still find the paths to it. And you can see how the best, worst, and average take slightly different paths through the city to get to the end. Okay, so your job and the code that you're provided with. So he provides you 2 program files for you, and you're not allowed to modify either of these. They are the city map header file, which defines the classes intersection, road segment, and city map, which you'll be using. And he also includes the city map base object file and CVP file, and this implements the main and the printing functionality of the city. So you don't have to worry about the command line arguments or printing or graphing the cities. So your job is to write the citymap.cpp, and this is the file you'll be turning in. And you're to implement the constructor for citymap, which will build up the graph of the city using the city intersection definitions coming in on standard input. And you may assume that there are no errors in the citymap input. The second function you're to write is Dijkstra, and you'll implement the Dijkstra shortest path algorithm to find a path from the first node to the last node. And you may assume that you can always reach the last node from the first node. So you don't have to check for the case where you can't actually reach the end. The argument that you're given is an integer, and it's a character A if you want the average time through the city, B for the best, and W for the worst. The Dijkstra function should return the distance of the shortest path, and it should put the path that it took inside the path variable. So when you write the citymap.cpp, you can compile it with this function, or you can use the make file that's in the lab directory. When he creates the lab, he's going to pipe the output of the city map using the print argument to sort. And this will sort all of your adjacency lists, so it doesn't matter what order you put the adjacencies from the intersections for the streets. So those will be sorted before they're compared. And then for the grading examples, all of the intersections have unique light durations and city links or edge links. This means that there's only one answer to the correct path for best, worst, and average, which prevents there ever being a duplicate correct answer. So that way you don't have to worry about, like, if you find a path, it's going to be the right one if you did the algorithm right. Note that in City 3, there is multiple best and average paths, so if you're comparing it to example 3, you might have different output, but it's still correct. So here is the city map header. It defines the intersection, and it also has an enum for road type, which defines if it's a street or an avenue. So your first 5 fields of the intersection are the input values, which are the street number that's part of, the avenue number, X and Y coordinates of the street light or the intersection, and then the green durations. And the green durations are indexed by road type, and road type, which is the enum street or avenue. So when you're indexing into green, you can use street or avenue to pull out the correct time. And then also you have the adjacency list, where you build up an adjacency list of the road segments going from this intersection. And the best time, back edge, and VF, SQ, pointer are all for performing the Dijkstra algorithm. And again, it doesn't matter what order the order of the adjacency list. The next class is road segment, and it makes up edge objects. And the type represents if it's part of a street or part of an avenue. Number is which street or avenue it's part of, and then distance, which is the distance along that road segment. You also have 2 pointers, from and to, which tells you where the intersection that it comes from and the intersection the street goes to. The last class is the city map class. It has the constructor and Dijkstra, which you'll implement, and it also has print and split JGraph, which are already implemented for you. The other things to note is that it has a pointer to the first intersection and a pointer to the last intersection, and you'll have to set these in your constructor. It also has a list of all, which is all the intersections in the city. And by adding intersections to the all list, that's what the print function uses when it prints out all the intersections. So that's how. So you don't have to implement the print, you just have to add the intersections to the all list in order for them to be printed out. And then the other thing that's important is the BFSQ, which is used for performing Dijkstra, and path list, which are used to store the path that you take through the city. And then some help getting started. He recommends that you start off by implementing Dijkstra to do nothing but return 0. This will allow your code to compile so that you can work on the constructor. And then work incrementally on the constructor. First write code that will read in all the lights, create the intersection classes, and put them into the all without worrying about the adjacency list. That way you can run the program with none print, and it will print out all the intersections. Once you have that working, you can add the edges and run print again. And doing all the edges is a pain, so he recommends using a temporary 2-dimensional vector of intersections indexed on like avenue number and street number, which allows you to pull out the intersections that you're connecting to make it easier to build up all the edge connections. And then once he's done, you can discard the temporary 2-dimensional vector because you don't need it anymore for performing Dijkstra. Then when you're done with it, done implementing the constructor, none and print should work and it should match his output. Then you can implement Dijkstra, and writing Dijkstra is easier than setting up the graph. So once you get the graph set up, you've done the hardest part, and now you just have to implement a Dijkstra algorithm to find the path to it. And then another recommendation is to create a function that will calculate the distance so that you can just keep calling a distance function instead of having to calculate the distance in line when you set up the edges. I think that's about it, all that I have. Do you have any questions?